Let's look at the remainder theorem, a very important theorem in our class. If the polynomial f of x is divided by x minus k, the remainder is equal to f of k. Let's see how the remainder theorem works in our example 1. In example 1, we had f of x equals 5x cubed minus 6x squared minus 28x minus 2, and we were dividing it by x plus 2. Or we can convert it to x minus a negative 2. The remainder here was negative 10 if you go back and look at the problem. So if I use the remainder theorem, it says if we substitute negative 2 in for f of x, we should get the remainder. If I take f of x and plug in a negative 2, I should get a negative 10 as my answer. So let's try f of negative 2. That's equal to 5 times negative 2 cubed minus 6 times negative 2 squared minus 28 times negative 2 minus 2. And then we're going to simplify the powers first. We have negative 2 cubed is negative 8, so this is 5 times negative 8. Negative 2 squared is positive 4, so this is 6 times positive 4. And then we have negative 28 times negative 2, which we'll simplify later, minus 2. So now let's do the products. 5 times negative 8 is negative 40. Negative 6 times 4 is negative 24. Negative 28 times negative 2 is positive 56 minus 2. We can simplify this with a calculator and we get negative 10. So the remainder theorem implies that f of negative 2 is equal to negative 10. So if I'm dividing by x plus 2, then f of negative 2 is going to give us the remainder negative 10 in this case. Again, if I divide by x plus 2 to my polynomial, that would imply that f of negative 2 equals negative 10. So think of the opposite when you're using x plus 2. It's actually implying f of negative 2 equals negative 10. In example 2, let's let f of x be equal to negative x to the fourth plus 3x squared minus 4x minus 5. Use the remainder theorem to find f of negative 3. Of course, we could plug in negative 3 into the function value and then evaluate it and figure out what f of negative 3 is. But we want to use the remainder theorem in this case. So let's use synthetic division. We're going to divide this function by x plus 3. Now I'm looking at the powers. This is a power of 4. I'm missing a power of 3. 2, 1, 0. So we are only missing a power of 3, so we need a placeholder. Using synthetic division, we're going to put a negative 3 in the front. And remember, we always use the opposite of what we're dividing by. In this case, we're dividing by x plus 3, so we're going to use negative 3 as our divisor. And then we'll put our coefficients. We have negative 1, 0, 3, negative 4, negative 5. We have to put 0 because we do not have a cubic term, so we need a 0 as a placeholder. We'll use synthetic division. We'll bring down the negative 1, and that gives us negative 1. We'll multiply negative 1 times negative 3. That gives us a positive 3. Then we'll add 0 plus 3 is 3. Then we'll multiply again. Negative 3 times 3 is going to give us negative 9. We'll add 3 minus 9, and that is negative 6. We will multiply now. Negative 3 times negative 6 is positive 18. Then we'll add negative 4 plus 18 is positive 14. Then we'll multiply negative 3 times 14, and that gives us negative 42. We'll add, and negative 5 minus 42 is negative 47. So according to the remainder theorem, we have f of negative 3 is equal to negative 47. Testing for potential zeros. A zero of a polynomial function f of x is a number k such that f of k equals 0. The real number zeros are the x-intercepts of the graph of a function, so they're going to touch the x-axis. The remainder theorem gives us a quick way to decide if a number k is a zero of a polynomial function defined by f of x as follows. We can use synthetic division to find f of k. If the remainder is 0, then f of k equals 0, and k is a zero of f of x. If the remainder is not 0, then k is not a zero of f of x. A zero of f of x is also known as a root or a solution to the equation f of x equals 0. Decide whether the given number k is a zero of f of x. All I have to do is show that f of 1 is going to be 0. Then that implies that this is a zero of f of x. So we're going to use the remainder theorem, and we're going to divide our function by x minus 1. So let's use synthetic division. Again, we're going to take the opposite of this, so that's positive 1 here for our divisor. And we're going to write the terms inside the dividend. We'll check to see if there's any missing powers. We have a power of 3, 2, 1, 0. So we don't have any missing powers. The coefficients are going to be 1, negative 4, 9, negative 6. So we'll use synthetic division. The first step is always to bring down the 1, and then we'll multiply. 1 times 1 is 1. Put the 1 underneath the negative 4. Negative 4 plus 1 is negative 3. Then we'll multiply again. 1 times negative 3 is negative 3. Then we'll add 9 minus 3. 9 minus 3 is 6. And then we'll multiply again. 1 times 6. 1 times 6 is 6. And then we'll add, and we get 0. So according to the remainder theorem, f of k will give us our remainder r. And in this case, we're using a 1. So f of 1 gives us a remainder here of 0. So f of 1 is 0. F of 1 is 0. And therefore, k is a 0 of f of x. Example 3. Decide whether the given number k is a 0 of f of x. Again, all we have to do is show that f of negative 1 is equal to 0. So let's use synthetic division. We're going to divide by x plus 1. Again, we use x plus 1 because that's the opposite of the value k that we're going to use. So let's set up our synthetic division. I'm going to use negative 1 here in the divisor. Let's look at the powers here. We have a power of 4, we're missing a power of 3, we have a power of 2, 1, and 0. So we're going to need a placeholder for the cubic term. So we have 1 for the leading coefficient of x to the 4th. There's no cubic term, I'll put a 0. In front of the x squared is a 1. In front of the x is negative 3. And we have a coefficient of 1. So we'll start with synthetic division. We'll bring down the 1. That gives us a 1. We'll multiply negative 1 times 1. That's negative 1. And then we'll add, we get negative 1. Then we'll multiply. Negative 1 times negative 1 is positive 1. And then we'll add positive 1 plus positive 1 gives us 2. Then I'm going to multiply negative 1 times 2, and that gives us negative 2. We'll add negative 3 plus negative 2, and that is negative 5. Then we'll multiply negative 1 times negative 5. Negative 1 times negative 5 is positive 5. And then we'll finally add 1 plus 5. That gives us a value of 6. This 6 is our remainder. So we know from the remainder theorem f of negative 1 is equal to 6. And therefore, we have that k equals negative 1 cannot be a 0, because it does not cause our function to be equal to 0. Decide whether the given number k is a 0 of f of x. Here we have f of x equals x to the 4th minus 2x cubed plus 4x squared plus 2x minus 5. It does not need a placeholder. We have a power of 4, 3, 2, 1, and 0, so we don't really need a placeholder. So let's use synthetic division when k is equal to 1 plus 2i. So we'll have 1 plus 2i here as our divisor, and then we'll write our coefficients. We have 1, negative 2, 4, 2, and negative 5. First step is to bring down the 1, and we have a 1. Next, we're going to multiply 1 plus 2i times 1. 1 plus 2i times 1 is going to give us 1 plus 2i. I'm going to add negative 2 plus 1 plus 2i. And negative 2 plus 1, that's just going to give us negative 1 plus 2i. Now we're going to multiply 1 plus 2i times negative 1 plus 2i. I'm just going to do the scratch work here on the side. 1 plus 2i times negative 1 plus 2i, we'll have to FOIL. 1 times negative 1 is negative 1. 1 times 2i is 2i. 2i times negative 1 is negative 2i. And negative 2i plus 2i is 4i squared. This simplifies to negative 1. The 2i and the negative 2i cancels out. And remember, I squared is equal to negative 1, so 4i squared is negative 4. And we have this is equal to negative 5. So when we multiply 1 plus 2i times negative 1 plus 2i, we're going to put negative 5 here underneath the 4. 4 plus negative 5 is negative 1. Then we multiply again. Negative 1 times 1 plus 2i is negative 1 minus 2i. We'll add 2 plus negative 1 minus 2i now. And that results in 1 minus 2i. Now I have to multiply 1 plus 2i times 1 minus 2i. So we'll do the scratch work on the side here. 1 plus 2i times 1 minus 2i. We'll have to use foiling, or if you notice, these are in fact conjugates of each other, so I can use the shortcut. The first with the first times the last with the last. And so we have 1 times 1 is 1, and 2i times negative 2i is negative 4i squared. Remember, I squared is equal to negative 1, so negative 4i squared is actually plus 4. And we have this is equal to the value of 5. So we'll put the 5 underneath the negative 5, and then we'll add. This gives us 0. So this is our remainder. So by the remainder theorem, we have f of 1 plus 2i is equal to 0. And therefore, 1 plus 2i is a 0 of f of x. Now, using synthetic for this one is a lot easier than trying to plug in 1 plus 2i into x to the 4th minus 2x cubed plus 4x squared plus 2x minus 5. It's a lot easier to use synthetic division instead.